Okay. All right. I think it's the magic time, whatever the time is. And I guess you can now, drink your boba tea or, enjoy yourself, while sipping some of your favorite drink, maybe like water or, something else. Anyway, I think we're ready. What do you think, Anna? I think we're ready. All right. Let's do it.
Welcome, ECS 16A. Woo!
All right. Well, today we're going to talk about vector spaces. And when we talk about vector spaces, let's talk about what we did last time. So last time, we continued talking about matrix transformation, and then we talked about matrix inverse, and we demonstrated how a matrix can be inverted and in what situation it can, and some situation it can't. And today we're going to go over some a lot of definitions, I have to say, quite a bit of definitions. So you have to bear with me. I'm glad I'm recording this and not like doing this in live because you have been probably like, when we're done. So yeah, so now you can kind of go back, revisit, watch it a few times. We'll see what happens. We're going to talk about vector spaces. We're going to talk about null spaces and subspaces, and we'll see what happens there. All right. Just a little bit of overview of what we've done before. We talked about matrix inversion. In particular, we said, if there's an operator, a linear operator that operating on a vector x, well, there is an inverse if it's possible to undo this operation, recover x from the result. So if I staple x and on unstaple, I get back x. So that would be an inversion. In particular, for linear systems, we can represent them using matrices. And so the question is whether a matrix has an inverse or not. For the scalar case, when you have, let's say, a times x, well, that may have an inverse if a is not equal 0. But if it for a matrix case, well, that can be a little bit more complicated. And that's what we've talked about before. And we talked about this particular theorem that says if a is invertible, A is invertible if and only if the columns of A are linearly independent. Okay, the columns of A are linearly independent. In that case, if the columns of A are linearly dependent, in that case, and if the columns of A are linearly dependent, then A to the -1 or the inverse of A does not exist. And if the inverse of A actually exists, well, that means that the columns of A are linearly independent. And then we did a proof concept, and the proof concept basically says that we assume that there is linear dependence and we assume invertibility, and then we show that there is a contradiction, and then we went all through that, and I just don't want to do it right now. You can just go back and watch the video from the previous time, so I don't have to do that in this video. I then gave you some example of a really useful solutions that you don't have to go through Gaussian elimination in order to do this. So if you want to compute an inverse of a 2x2 matrix, what you do is you flip the A and D, negate B and C, and then divide the whole thing by AD minus BC. And so this is the equation. And this is really, really, really useful to remember. Anna, how useful is it to remember? Really? Yep. You heard, Anna? It's really useful. So you should remember that one. Okay. And how you derive this? Well, you basically go through this and do Gaussian elimination, right? Like the usual thing where you go like A, B, C, D, and then 1, 0, 0, 1, and then you do Gaussian elimination to that, and then you would get this. Okay. All right. Any questions? You're also quiet today. All right, well, let's move on. Oh, that's great. All right. A few equivalent statements with respect to invertibility, and not all of them we've covered. So in particular, we're going to cover some of these today, but I just want to emphasize those. These are all equivalent statement. So a matrix A is invertible. that also means that AX equals B has a unique solution. What does it mean AX equals B has a unique solution? Well, it also means that A has linearly independent columns. And that also says that A is full rank. Now, what's rank? We haven't talked about that, but we will in a second. It also says that A has a trivial null space. What is a null space? I don't know. Well, we're going to define this today. And finally, it says that the determinant of A is not 0. What is the determinant? Well, that you have to wait till Tuesday. Okay, so not that. But all of these are equivalent statement. But effectively, it means that there is only one mapping from a vector to the solution. So if I take X and I push it through A and I get a B, if I want to go back, there's really just one B that will be generated. And there's no arbitrary solution that can be generated. And if there's just one, then I can invert this particular system of equations. All right. Okay, so today and next time, we're gonna develop some jargon. We're gonna talk about rank. We're gonna talk about null spaces. We're gonna talk about vector space and subspaces and bases and dimension and column space and row space, all that stuff we're gonna cover. So, just sit down and enjoy. All right. Now, why do we want to develop, and is this even jargon actually useful? So, I've kind of stared at this jargon and just kind of remember, wow, that sounds familiar. I work on MRI, right? So this is a kind of the field of medical imaging. I work, it's a machine that you can look inside the body. And, somebody would ask, like, why are we teaching all these notations? Well, here's just an example. This is a paper we wrote in 2014. It's a paper in the MRI field, okay? So it's a subfield of a subfield of a subfield. And you would think, well, why is all this linear algebra notation that we will learn is actually useful? Well, first of all, 834 citations, so that's pretty good in about 7 years or so. So it's not bad. It means that 834 papers thought that this is worth referring to. So okay, that's pretty nice. But this paper really, it has the basis. If you actually search this paper for basis, you get 3 times rank, you get 4 times row space, you get 4 times columns of the matrix, 6 times subspaces that we're going to cover today, 17 times null space, 29 times eigen 87 times. So all of these will be relevant. Let me figure out if I actually can go and go into this. Yeah, there you go. All right, so this is the paper. This is the paper, and we can kind of go and now search for stuff. So let's search for a null space. Okay, let's put null space over here. Null space, and fine, null space, and there you go. Null space, null space, null space. Going through, chugging along. All these matrix multiplications that you are used to seeing in the class. They all show up here. Keep going, keep going. Keep going. Oh, null space, some figures, some MRI pictures, null space, linear set of equations, null space, matrices, eigenvalue decomposition, eigenvectors, maps, and all that stuff, all the good stuff that we're going to cover in this class, look, are actually showing in a paper in a journal that is actually related to MRI. So obviously, there's other papers that are not least important in this. However, just want to give you, it's like this, if knowing all these notations is important, no matter really what field you are in engineering and computer science, because you'll be using those over and over again. So hopefully this is a good motivation for you to study at least those notations. All right. Any questions? No questions. All right. Okay. Well, let's try it and look at the first definition. So the definition is about a vector space. And what is a vector space? Okay, a vector space, from you open Merriam-Webster dictionary, it's a big thing. Actually, you don't open it anymore. You can actually go online. And then you go and says, definition of a vector space is a set of vectors along with operations of additions and multiplications such that the set is a commutative group under addition. It includes a multiplicative inverse, a multiplication with a scalar that is both associative and distributive. All right, well, what does it really mean? Well, we're going to go through all of these requirements. So a vector space is a definition. Okay, these are axioms that we said, if you have some vectors and a set of them, what does it mean to have a vector space? It is a definition. Okay, and we're defining it, and then it will have nice properties that we can then use them to do other things once it's a vector space. Okay, we can use if we can define something as a vector space, then it will have nice properties. So here's the definition. A vector space is a set of vectors and scalars. Okay, so some vectors that are in Rn and some scalars that are in R, and two operators. The first one is multiplication and addition that will satisfy the following 10 requirements. Okay, we're going to go like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, 10 requirements. The first one is that if you scale the vector x, okay, it is also staying within this vector space. So any scaling of the vector still keeps you in the vector space. Okay, well, that's again definition 1. Definition 2 says that if I take two vectors, x and y, that are in the vector space, and I add them both together, they will remain in the vector space. These two properties are the axiom of closure. So the vector space is closed under multiplication with a scalar and under addition. Okay, so the operation of multiplying by a scalar of a vector will keep us in the vector space. The addition of two vectors within the vector space will keep us within the vector space. Okay. All right, again, definition. Third one is associativity. That means that if I add three components in the vector space, three vectors in the vector space, if I first add the two and then I add the third to them, to the result, it will be the same as adding the first two first and then adding the third one. And that definition is associativity. Fourth, commutativity. It doesn't matter the order of addition. Okay, the addition order doesn't matter. I can do x plus y or y plus x. It will exactly be the same. Okay, that's a good one. There exists a vector 0 within the vector space. That means that 0, there is something called a vector 0 that is within the vector space, such that x plus this vector 0 will remain x. So basically additive identity, that's this, okay? Next one is the additive inverse. There exists some negative vector x that is still within the vector space, such that if I take x and I add it to its negative, then I would get 0. So this is additive inverse. And all of these are the axioms of the addition operator, right? We said the vector space is a set of vectors and scalars, vectors in Rn and scalars in R. with operators multiplication and addition. So this is the axiom for the addition. So now let's go for the axiom of multiplication. And the first one, which is number 2, 3, 4, 5, 6, 7, it says the following. If I add x plus y and I multiply it by a scalar, it is the same, and of course x and y are within the vector space. It's the same as taking x and adding by a scalar, taking y adding by a scalar, multiplying by a scalar, and then adding them together. And this property is called distributivity. Finally, we're getting close to the end, so bear with me over here. Here's the following. If I have a beta, some scalar, times my vector, x, I compute beta times x, take the result and then multiply by alpha, is the same as taking alpha, multiplying by beta, taking the result, and then multiplying by x. Okay. All right, again, a definition. This would be the requirements. The nice thing about a vector space, it will have different really good properties that we'll be able to use to prove other things. So once we can define, let's say if something is part of a vector space, we could use it. But in order for it to be in the vector space, we have to have all these definitions. All right, this one is a good one too. If I have alpha and beta, which are scalars, and I add them together, and then multiplying by some vector in the vector space, that's the same as taking alpha and multiplying by the vector, taking beta, multiplying by the vector, and then adding the result. And finally, is the last one. There is a vector 1 or some scalar 1 such that if I multiply it, so not a vector, scalar 1, that when I multiply it by the vector x, I will stay and get the vector x. Okay, these are the axiom of scaling, or the multiplication, or the multiplication operators. Okay, all right, we're done with definition. Now this is the definition of vector space, and now we can test if something is a vector space. So let's go to some examples. And our examples are going to be the following. Let's ask this: is R2, all the vectors in R2 belong to a vector space? So is R2 a vector space? Well, what you have to do is to go through all those operations and see that if a vector is in R2, would belong to a vector space. Okay, so let's just do a first one. If I have some vector x in R2 and I scale it by alpha, would it stay? Yeah, it would, right? If I have just vector, in R2, I multiply by scalar, yeah, it would. What about adding those two? Of course. If I have one vector in R2 and another vector in R2 and I add them together, of course they'll stay in R2. So R2 is a vector space. You can go through all of these and show that this is the case. All right, so great. We're a happy chunk. Now, what about matrices? Well, matrices are pretty much a combination of two vectors, one next to each other. So in R2 by 2, and the question is R2 by 2 a vector space? And of course, you can go through all of these. And since R2, which is just the space of one vector, is a vector space, it's pretty obvious that if I add two more numbers, it will still be in the vector space. So I can go, again, I go through all of these and show that yes, a matrix that is 2 by 2, all the matrices that are 2 by 2 are a vector space. It's a vector space. Okay, great. What about this one? What about this one? Let's say alpha is a scalar. Okay, alpha is a scalar in the reals, but we also limit alpha to be only on the positive axis. Is this a vector space? Okay, I'm gonna wait for an answer here. What do you think? Is alpha a vector space? Hmm? Well, let's look at this case. Um, what about this one? What about 6? There exists a minus x that is within the vector space, such that x plus minus x equals 0. Okay, so if we have some alpha, do we have a minus alpha that's within the vector space? Do we? Well, it says that alpha has to be 0, so there isn't really a minus alpha. Hence, there is no minus alpha in the vector space, such that x plus such that alpha plus minus alpha would equal 0. Hence, this is not a vector space. Okay, this set is not a vector space. All right, so let's put the party parrot police over here. All right, let's move on. What about the span of 0, 1? Okay, is that a vector space? Okay, so what is the span of that? Is all the vectors? It's all the vectors that I can represent using alpha 0, 1 times 0, 1. All these. Okay, well, if you actually go through and says, well, is multiplying 0, 1 by some alpha? Yeah, that will be still in the vector space. What about adding 2 of them? Yes, because it will be, yeah, you can show that. Actually, it's pretty easy to show. This is very easy to show. Is there a 0 such that x plus 0 equals that? Well, yes, when alpha equals 0, then it's still within the span. What about a negative? Well, yes, if I have a negative alpha times that, it's still within the span of alpha 0, 1. And so I can actually come up with a negative x, and so on and so forth. So yes, the span of 0, 1 is a vector space. Mickey Party Parrot. All right. All right, what's the next one? Next one is the vector 0, 1, though, a vector space? I mean, the span is, but is this vector is? Well, the vector is just fixed. So it cannot be a vector space because, of course, for example, negative x is not 0, 1. Okay, so it definitely doesn't satisfy this one and doesn't satisfy anything, actually. If I multiply alpha by x, I would not get 0, 1. If I multiply by 2, I will get 0, 2. 0, 2 is not 0, 1. Hence, the vector 0, 1 is not a vector space. The span of 0, 1 is, but the vector isn't. Okay. All right. And so, yeah, party parrot police. And the last one is 0. Is 0 a vector space? That's interesting. Let's see. 0 times alpha is 0. Yep. Well, 0 plus 0. Yep. Okay. Because it has to be in the vector space. So 0 plus 0. Yep. That's true. What about here? All these zeros? Yep. What about here? Yep. Zeros are here. There exists a 0 in the vector space? Yes, there is one. If I take 0 plus 0 equals 0, yep, that works. What about a negative 0? Yeah, there's a negative 0. That's still in the vector space because it's 0. And then 0 plus minus 0 equals 0. Yep, that's true. And what about here? I'll take x being 0 because that's the only one, and y being 0. Yeah, that's the only one. So yeah, that works. And what about this one? Beta times 0 times alpha is 0. It's the same as whatever alpha and beta times 0. Yep, that's a 0 and 0, and so on and so forth. So 0 is a vector space. And also all the 0 vectors. Okay, so for example, 0 in R2, 0 in R3, 0 in Rn are vector spaces. All right, well, whew, that was a lot of definitions over here. So we're just going to keep going. We're going to keep going. Okay, once we have this vector space, What about defining what's called a subspace? Remember in that paper, there was a lot of subspace too. Okay, that's good. Well, let's define a subspace. What's a subspace? Well, a subspace U consists of a subset of some subset of V in a vector space VF plus dot, right? This defines a vector space. So U consists of just a subset of those set. Okay? In a more clear definition, says that U is a subset, this magnet here, symbol is a subset of V and has three properties. So U is a subspace and it's a subset of V if it has the following three properties. The first one, it must contain the zero vector. Okay, so zero must be in U. If zero is not in U, do this thing with your ears. Ow. All right. Woke you up, huh? All right. Zero must be in a subset. Now, a subspace is closed under addition. So if I have V1 and V2 that are both in U, if I add V1 and V2, I will still be in the subspace U. Okay. All right. And the last one, it's closed under scalar multiplication. So if V1 is in U and alpha is in F, which is just the set of the real numbers, then alpha times V will still be in this subset. Okay, and we're talking about a subset of a vector space, a subset, a part of it. Okay, well, I mean, this is quite confusing, even to me. So I think we should look at some examples. Okay, let's look at some examples. Let's see. R2 is a vector space, right? So R2 is a vector space. So now let's consider a subset of vectors in R2 such that the length of them is less than 1. Is it a subset of V? Okay, so all vectors V that their length is less than 1. Is this a subset of R2, which is the vector space V? Is it? Well, definitely it is a subset. Basically, it's all the vectors within this unit circle. Okay, all the vectors that are within the unit circle here will satisfy that. Okay, so that's a subset. Okay, so yes, U is a subset of V. Okay, that's the first thing, but it needs to have three properties. So it doesn't contain zero. I think so, yeah, because, you know, zero is within the set. So yeah, which color? Oh, I'll pick this one. All right, contains zero. Let's see. Is it closed under vector addition? That is, if I pick some two vectors, V1, let's say this one, and then V2, let's say this one, and then I add them both together, is this still within the subset? Okay, let's see. Well, I'll add these two, and I would get this vector. Okay, do it with your ears. Oh, no, it is not closed under vector addition. Would it be, by the way, closed under vector, under scalar multiplication? No, of course not, because if I scale it, it will just, we'll go up here and we'll come out of the set. So no. So the subset of all vectors, V, whose length is less than 1, is not a subspace. It is a set, but it's not a subspace. Okay, so not closed under addition, nor scalar multiplications. Any questions? No questions. All right, let's move on. Let's move on. This is so clear on this lecture, huh? All right. Oh, that's a good one. That's a good one. Is the span of the vector 1, 1 a subspace? Now, what does it mean? Span of 1, 1? Well, it's all the vectors will linear combination of A times 1, 1, right? Anything that I can represent by A 1, 1, is this a subspace? Okay, so basically it's anything along this line. Anything along this line, any vector along this line would be considered within that set of a span. And the question is this a subspace? Okay, let's see. Does it contain 0? Yes. Oh, thanks, Jimmy. Is it closed under vector addition and multiplication? Sorry, under vector addition? Well, let's see. All right, let's pick this vector. And then let's pick this vector. They have to be within the subset and then add them. Well, it will stay, it will not move from this line. So I would say, yes, it is closed under vector addition. And what about closed under vector multiplication? Well, that's pretty easy too. What you do, let's take this one here over here, and then scale it by a factor of 1 billion. And if I scale it by a factor of 1 billion, then I would get let's keep going, but it's still going to be along this line. So the answer is yes. The answer is yes. The span of 1, 1 is a subspace. Okay, check. Before, we didn't get a subspace. Now we have a subspace. Okay, well, now the question is like, what about this line? What about this line? Is this a subspace? Kind of looks the same, right? Well, I would argue that if we check the first thing that says contains 0, well, it doesn't. So do with your ears. Ready? 3, 2, 1. Nope, it is not a subspace, right? Because 0 is not within the set. Hence, this is not a subspace. Cool, huh? That's a lovely definition. All right, let's get it more complicated. What about this one? Okay, the set, this really nice cone. It looks like, it looks like what comes out of a neutron star or like a black hole. It's like stuff kind of in cones on both sides, like the material ejected. Pretty awesome. Is that a subspace? Well, let's see. Is 0 contains under yeah, 0 is there. Let's go to 3. Is it closed under scalar multiplication? Oh, let's see. We take pick a different color. Yeah, scalar multiplication. I take this vector and I scale it. Yep, that will be within the set because it will be yeah, and everything actually, if I just rotate, any vectors will stay within the set under scalar multiplication. Okay, so yes. What about vector addition? What about vector addition? Well, let's see. Let's take this one, this vector over here. And then, let's take something else. So this is along the boundary of the set, but let's take this boundary over here. So let's take this vector also, and let's add them both together. That was close. That was close. So, ready? 3, 2, 1. Nope, not closed under addition. Okay, so this is not a subspace. It is a set. This is a subset in U. Sorry, it's a subset in the vector space B, but it is not a subspace. Subset, not a subspace. Okay, now the thing is, why do I care? Well, again, subspaces have nice properties that if we can prove that something is a subspace, we can use those properties. Okay, so what about each one of those 2D planes? Okay, 2D planes or this line out of R3, are these vector spaces? Sorry, are these subspaces? Well, yes, because a plane will contain 0. So as long as they go through the 0, if it was a plane that's cutting, that it doesn't go through 0, no. But if it goes through 0, yes, it will be. What about vector addition? Yeah, if I have a vector within the plane, 2 vectors within a plane, they'll stay within the plane. What about scalar multiplication? Well, if I have a vector inside a plane and I scale it, it stays within the plane. So as long as these are crossing 0 or passing through 0, then we should be okay, right? So yes, planes out of R3 are vector spaces. Okay? Planes, not manifolds or something else. Those would not be a subspace. However, a plane out of R3 would be. What about a plane of in R4? What about? Do you want to draw it? I'm not going to draw it, but yes, a plane in R4 would also. What about a line in R5? Yeah, right. So you can go and prove all of that stuff. I'm chugging along. Okay, let's look at another example. All right, so just like it's clicks. Let's say that W is the subspace of all matrices, 2x2 matrices, such that you have A, B, 0, and D, and these are scalars. And this is a subset of a vector space that we showed before, or we claimed to show before, that is in R, that represents R2x2. And the question is this a vector space? No, Mick. Is this a subspace? Is this a subspace? Okay. All right. So what do you think? I don't know. What do you think? Come on. I don't know. But what do you think? Let's check. All right, let's check then. And let's check. I just freaked out. I thought I'm not recording this. And I had this moment. And now my face became white. And because I thought it was like, no, but then I opened the thing, it goes like pause recording. So it means that we're recording. So we're okay. It's like, oh, it's one of those moments. You remember that day when Zoom crashed all the time? Whew. Well, let me just get a breath for a second. Okay. Oh, Mickey, you're okay. You're okay. Just continue. Okay. All right. Well, let's just continue then. All right. Let's see. Let's check. Is the 0 vector part of that subset? Well, 0 vector. It is 0, 0, 0, 0. Yeah, I would argue that's within A, B, 0, D, right? If I set A, B, and D to be 0, yeah, it is. Okay, yeah, beautiful. What about closed under addition? Okay, well, let's see if it's closed under addition. Let's take two vectors or two matrices. Let's take I don't know, A1, B1, 0, and D1, and then add it to A2, B2, 0, and D2. What do I get? Well, I would get A1 plus A2, B1 plus B2, 0 plus 0, and then D2 plus D1. All right, check. And what about a closed under scalar multiplication? Well, let's see. If I take this and I scale it, it will still have the same shape. So yes. Woohoo! That is a vector space. That's a vector space. And sorry, that is a subspace. That is a subspace. Okay. So effectively, all the matrices that are upper triangular are considered a subspace. Okay, all the matrices that are upper triangular are a subspace. Subspace of what? Well, all matrices that are n by n, for example. Great. Let's move to another definition, basis. Quickly, it's actually pretty simple. In words, a basis is the minimum set of vectors that spans a vector space. So if I have a vector space, let's say Rn, I need a minimum set of vectors that the span of it will cover Rn. Okay, so let's look at R2. What's the minimum vectors? Set of vectors that would span R2. Is 1 enough? No. Is 2 enough? Yes, that's it. We need to find 2 vectors that would span it. Those 2 will have to be linearly independent for this to happen. Okay, so it's a minimum set of vectors that spans that vector space. So definition, given a vector space and a set of vectors v1 to vn within this vector space, these v1 till vn is the basis of the vector space if it satisfies the following. v1, v2, and all this set are linearly independent. And what is this opposite A? Well, that basically says for all, okay, or for any. For any vector in the vector space, remember the E? There exists, okay, so let's write it down. For any, and this is there exists some scalars, alpha 1 till alpha n, that are in Rn, such that if I take a linear combination of all of these, okay, all of these, they would result in this vector V, no matter what V is. So V could be an arbitrary vector in that vector space. I can reach it by a linear combination of these vectors. That means that V is in the span of this set. Okay, as long as that means that the set of V's can be defined as a basis for the vector space. Okay, so let's do some example of bases. Okay. Is 1 0 0 0 1 0 0 0 1 a basis for R3? Is the span of these 3 vectors, okay, is the span of these 3 vectors R3? Are they linearly independent? Yes. Woohoo! What about if I replace this 1 with a 10? Can I still reach any vector in R3? Yes, I can. Are these linearly independent? Yes, they are. Here you go. And what about this? Well, you can easily show that, yes, absolutely, you can go in R3 and do a linear combination of these and reach any point. And also, these are linearly independent. Because if I try to represent this vector. By these two vectors, I won't be able to. So they are linearly independent. Hence, yes, these are all bases for R3. So there's many bases for R3. This in particular one is called the identity basis, or the trivial basis, because it has only 1, 0, 0, 0, 1, 0. It uses the E vectors, remember? Okay. All right, well, what about this one? What about this one? Well, is this a basis for R3? Well, definitely R3 is within the span of these vectors, right? Because it's within the span of this, and definitely within the span of that, of all of these. So is this also a basis for R3? And the question is, well, are these linearly independent? And they cannot be linearly independent because this one can be represented by a linear combination of these. So they're not linearly independent. Hence, this is not a basis. It's not the minimum number, right? Like 4, like it's enough, 3 are enough in order to represent the basis. 4, it's too much. So it's not a basis anymore. Okay. What about 1, 0, 0, 0, 10, 0? Is this a basis for R3? Ready? Cover your ears. No, it isn't. Why it isn't? Well, because I cannot reach the entire R3 by just a linear combination of two vectors in R3. I can't. These only represent a plane in R3. They're not a basis. There'll be maybe a basis for a subspace, but they are not a basis for R3. Okay. So the answer is no. Okay, we're chugging along all these definitions. Pretty exciting, pretty exciting. Let's go back to span. Remember the definition of span? Well, the definition of span is that the span of a set of vectors is pretty much, what's going on here? Yeah, it's pretty much that a linear combination of all of these vectors. Yeah, it's the span of, you're right. Okay. The span of all these vectors is basically anything that I can represent, any vector that can be represented by a linear combination of all of them. Okay. So I got something here kind of like annoying, but okay. So it's just anything that I can represent by a linear combination of these vectors. That is within the span. Okay. It is also called the range. It is also called a column space of a vector. So the span of the columns of a matrix, or the column space, or the range of a matrix is a set of all vectors that would result in this possible linear combination. So let's look at an example. Let's say I have a matrix A, and the matrix A looks like this. And the matrix A looks like this. And the question is, are the columns of A a basis? Are the columns of A a basis? Are they a basis? No, they're not a basis. They're not a basis because these are just two vectors in R3. We already showed this is not a basis. But are the columns of A form a basis for a subspace? So is the span of the columns of A, or the column space, is a subspace? Okay, it is a vector space. Okay, so is it a subspace? Again, let me rephrase. Do the columns of the span of the columns of A are a subspace? Well, let's see. We have to check. We have to check if this is true. So let's go and check. Okay. Let me define a few things here. First of all, we define A. Okay, that's the matrix that we want to evaluate if the column space is a subspace. So basically the space spanned by the columns, these two vectors. And so let's say now define the following thing. Let's say we have some U1. What's the dimensions of U? U is an R 2 by 1, right? It has to be because like this and like that. And the size of this has to fit. So U is in R2. And when I multiply the vector, U1 by A, I would get V1, which is a vector of length. What is V? V1 is a vector of R 3 by 1. Okay, so it's in the reals of 3 by 1. Okay, now is V1 within the set? Yeah, it has to be because it's within the span. Is V1 within the span of these two vectors? Absolutely, because by definition, if I multiply A by U1, it's a linear combination of the columns of A, and hence V1 is a linear combination of the columns of A. Hence, it's within the range, it's within the span of the columns of A. Okay, just by definition. What about V2? Well, V2 is some A times U2, which is some other vectors. Yes, and V2 is also within the span of the columns of A. It's within the range. It's within the column space. And the question is this a subspace? Well, we have to check. What about zero vector? Does zero vector exist there? Well, let's multiply. Let's take A, okay, and multiply by 0. And I would get 0. Okay, so 0 is within the column space. I can represent 0 by by a linear combination of these two columns. How? I'll take the first column, multiply by 0. I'll take the second column, multiply by 0, and add them together, right? That's a linear combination, and I would get 0. So yes, it is. Okay, let's pick a different color. Now, is it closed under addition? That's a good point. Well, let's take V1 and V2. V1 and V2 are within the span, right? It is a linear combination of the columns of A. And let's see if we add them together, are we still within the span of the columns of A? All right, let's see. We take V1 and V2. Well, what is V1? Well, V1 is A times U1 by definition. What is V2? V2 is A times U2. And by matrix, we know the properties of matrix multiplication. We can say that A times the sum of U1 plus U2, this is equal to the A times the sum of U1 plus U2. Okay, well, now you got yourself. So V1 plus V2 is the result, stays within the span of the columns of A, because now when we multiply by this vector, it's a linear combination of the columns, so it has to be within the span. And since it's within the span, then V1 plus V2 are also within the span. Okay, so yes, V1 plus V2 are also within the span. So yes, that is still correct. Perfimundo. And then what about scalar multiplication? Well, let's take that one and do alpha times V1. Is that within the span of the columns of A? Well, alpha times V1 is alpha times A times U1. But we know that it is the same as A times alpha times U1. Hence, this result is a linear combination of the columns of A, hence alpha times V1 is also a linear combination of the columns of A. It can be represented by a linear combination of the columns of A. and hence this is still within the span. So closed under scalar multiplication, and whoo-hoo, yes, it is a subspace. So the column space of a matrix is also a subspace. Okay, beautiful. Let's talk about rank. This is, for example, one ranking. Like if you look at the USA Today university ranking that just came out a few, maybe a week ago for Cal. Well, turns out we're ranked pretty high, so you should kind of go like, it's like, oh wow, good, I got into a great school. So number one in computer science, jointly with other 3 institutions. Number 2 in electrical engineering, also joint with another institution. And then 3rd in computer engineering. And the nice thing about it, well, I think you care about it more than I do. I don't care so much, but it's bigger or equal than Stanford. Okay, so you might be happy about it. I probably don't care. I did actually go to Stanford, but I just said that because probably there's a lot of cheering going on right now. I guess cover your ears again. That's right. Yep. Okay. Let's talk about real rank of matrices. Okay. All right. What is a rank? Well, if I have a matrix that is n by m, the rank of that matrix is the size, the dimensions, the size of the dimension of the span of that matrix. Whoa, hold your horses. Well, we said that the span of the matrix A is a subspace. So we're just going to look at the dimension of that subspace. Well, let's say the span of A is 2 vectors out of R3, then I would say the number of dimensions is 2, and hence the rank is 2. If the span of A, and let's say A is in R3 by 3, then, and the columns, if the span of A is R3 by 3, sorry, it's R3, the span of A is R3, then that also means that the columns of A are independent vectors. Well, then the dimension of the span of A would be the entire R3, which has 3 dimensions. So it will be a 3. So rank is just a number. So let's take a look. Let's take a look at the column space here. The column space here, we see that these are linearly independent. So it is a subspace, right? It is a subspace of, and the columns of A are within the span of 2 vectors, okay? Only 2 vectors, hence the rank of this matrix will be 2, okay? Just 2 vectors, linear combination of 2 vectors, that'd be 2. And these are linearly independent, so they represent a span of combination of 2 independent vectors. Hence the rank is 2. What about here? This is a 3 by 3 matrix, but how many columns are independent? Well, this is a 0 column, so of course only 2. So in the same case here, the rank of A is the size of the dimension of the span of A. The span of A is just a linear combination of 2 vectors, hence the rank of A is also 2. Right. Now, what about ABC 0, 0, 0, 0, 0, 0? What is the rank of A? Well, the span of the columns of A is just 1 dimensional, so just 1 dimension, hence the rank of A is 1. Okay. All right. Well, in general, the rank of A will be then the dimension of the span of A, and that would always be the minimum of M or N, which are the dimensions of that matrix. So it's always the minimum. So it can never, this matrix, which is 3 by 2, can never be more than 2. Okay, could be less, but it can never be more. This one is a 3 by 3, so it can never be more than 3. Okay, always less or equal to 3. In this case, it's less, and it will be 1. What about this matrix? 1 0 0 0 1 0 0 0 1. What's the rank of that? Well, the rank of that is 3. Okay, because the span of the columns of A span a 3-dimensional space, and hence the rank is going to be 3. All right, any questions? All clear. Beautiful. Okay, so now we get into the last part of the lecture, and we're going to talk about a null space. Remember how many null space were in my paper? Well, it's quite a few of them. I think 28, 29 times, because all about actually the null space of some matrix in MRI, which was pretty cool, but it was just, the paper was basically entirely based on that. Finding what is the null space, and what does it mean by null space? Well, here's the definition. The null space of a matrix, and it doesn't have to be square, could be rectangular. So in Rn by m, is the set of all vectors, okay? All vectors in what size? Well, it has to be Rm, because we're going to multiply a times x. In like this and like that, has to be that the matrix is Rn by m, hence the vector has to be m size. Otherwise, it doesn't work. That when I multiply a by that x, I would get 0. Okay, well, what about it? I want you to stare at this. I'm going to stare at this too. A times x equal 0. That is not trivial. Normally, when you look at scalars, a times x equals 0, it's pretty obvious what x is. X has to be 0. Well, would that be true if the vector x would be 0? Yes, it would be true. But for matrices, x does not have to be, the vector x does not have to be 0 for this to actually result in a 0 output. And that is something that is different between scalars and vectors. And it's a really important point. Okay. The question is, if I have this is a set of equations. So the null space, so all the vectors, x, that satisfy a times x equals 0. The question is like, how many solutions are there? Well, at least one. The 0 vector is, that works. The 0 vector works, but are there more? So how many solutions? Well, what we can do is effectively pose that as an optimization, and then try to solve it and see what happens. So let's look at an example. Here's an example. 1 0 0 2. Okay, 1 0 0 2. Multiplied by x1 and x2 equals 0. Okay, so a times x equals 0. And the question is, okay, what are the x1 and x2 that would satisfy that? Now, thing is, if you look at these two vectors, they're linearly independent. When you have linearly independent vectors, the solution for this linear equation is just one, is unique, right? It's just unique. And since it's unique, I can say, you know what? The only vector that will be true would be 0 0, because this has only a unique solution. It's linearly independent. Hence, there's one solution. And that solution has to be 0 0. If it's something else, then it's more than, 0 0 is always a solution. In that case, I would say, 0 is always a solution for this particular ax equals 0, is always in the null space of the matrix A. And this is called a trivial null space. So this matrix over here is set to have a trivial null space. That means that only 0 0 is within its null space would result in A x equals 0. All right, another example. What about this one? Well, 1, 0, minus 2, 0 times x1, x2 equals 0. Okay, well, how do we find the set of all these x's that would satisfy that? Well, again, we can, we see, oh, wait, we see that these are linearly dependent. So maybe there's more than one solution. Remember when we said that if the columns of A are linearly dependent, there are multiple solutions. So there will be more solutions. So let's do Gaussian elimination. I'll just do it quick, just for the sake of time. And you can just do it by yourself, and it's actually just one step. So we're just going to put in an augmented matrix: 1, minus 2, 0, 0, 0, 0. Oh, we have this row that's 0, 0, 0. So yeah, x2 is a free variable. X2 is a free variable. Hence, x1, I can represent x1 by a function of x2. So x1 equals 2x2. That's the equation. Hence, x, the vector x, any solution can be represented by this. If I have some alpha, by some alpha, which is the free variable, I can pick anything that I want. And then x1 will immediately become 2 alpha. Okay, so I have now a set of solution, x equals alpha times 2, 1. Now that is a set of solution because alpha could be 0, but it could be anything else. It could be, let's give another pi. Pi, it could be pi. It could be e. It could be my favorite number, 3. Oh, no, 2. It could be anything. So what I can say about this matrix, this particular matrix has a non-trivial null space. It's not just 0. And it is the span of the vector 2, 1, because any scalar multiplication of 2, 1 will result in a solution of this matrix A times that x, if x has this form, to be 0. So this is said to have a non-trivial null space. So sometimes we have a trivial null space. So every matrix will have a null space. But sometimes we'll have a trivial null space, which is 0. And sometimes we'll have a non-trivial, which will be something else. And now the thing is that span of some vector, we already showed that this is a subspace. So effectively, we can say a null space is the subspace of vectors spanned by this basis. Well, yes, that satisfies A times x equals 0. Okay? So the subspace, it's a basis for the subspace, or the basis of the null space. Okay, null space is a subspace. Okay, here's some other example. A times x equal b. A is an arbitrary matrix. B is a solution for this linear equation. X is something that is unknown. And let's say that A has a null space, that it's non-trivial. And let's say we know that V0 belongs to that null space, is within this null space. What does it really mean? Well, it means that A times V0 equals 0, right? Just by definition, if V is in the null space of A, then A times V0 is 0. Now let's say we know some solution about AX equals. Let's say there is a solution x0. X0 is a solution, and let's say we know at least one solution. There might be more, but we know one, and that solution is x0. What does that mean? Well, that means that A times x0 will equal b. Why? Because, well, it says A times x equals b. So if I found a solution for this, then A times x0 equals b. That's by definition. So here's something that we kind of did before. So here's my point. I would say that if I know that V is in the null space, and I know that X is a V0 is in the null space, and I know that X0 is a solution, well, I'm going to argue that this linear combination, X0 plus some alpha, V0 is also a solution. Ooh, interesting. Well, let's see. Well, let's put it and see if it's actually a solution. So A times x0 plus A alpha v0. Well, that's a vector composed out of a linear combination of two vectors. Well, in that case, I can just, by the rules, I can say, well, this equals to A times x0 plus A times alpha v0. Can I do that? Yeah, absolutely. Okay, well, what's next? What is A times x0? That's by definition B. So I'm going to replace it. Now, what is A times alpha v0? Well, I know that A times v0 is 0, but it's A times alpha v0. So let's just take the alpha out because we can. That is matrix vector multiplication. We're allowed to do that. So that equals B, and that equals to A times alpha times A times v0. But what is A times v0? That is 0. So I will just end up with B. So A times that gives B, and that is the solution. Hence, any vector that has this linear combination is a solution. So there's really infinite number of solutions. And I can then say K QED. And that's because of the radio station. Just don't use it. Okay, it's a joke. I know. It's pretty cool. All right, let's go back to tomography. Remember this problem with the meat that we try to image, and we said, oh, let's make projection, like 4 projections, like one here, and then another one here, and then we had this set of equations. That equals 4, equals 4, and this one, this plus that equals 3, and then this plus that equals 2, and then this plus that equals 5. Remember that? Second lecture or so. And then we put it in the augmented matrix where this was A, the matrix A, and this was the vector B. Remember? Okay, well, and we said, oh, it has infinite solutions and stuff. Remember? Okay, all right, let's go and revisit that in the context of a null space. Let's see. Well, what I'm going to do now is I'm going to try to find a null space, but you know what I'm going to do? I'm going to do exactly the same Gaussian elimination that I did before. The thing is with Gaussian elimination is this vector here doesn't matter what it is. Okay, it doesn't matter what it is. All the manipulations are done on A, right? This is the matrix A. So all the manipulations are done here. So it's the same steps. So I'm just going to go and do all these steps and end up with this result. And obviously, I have the last row being 0. So I have some free variable and then dependent variables. Okay. All right. Well, this is the matrix that I got. And obviously, x4 is the free variable, right? So x4 is a free variable. And since it's a free variable, I can now go and represent all the variables as a function of x4. So, okay, well, let's see. If I set x4 to be equal alpha, well, then according to this, x3 will be equal minus alpha. And according to this, x2 will be equal also minus alpha. And then according to this, x1 will be equal alpha. Okay, so let's just flip the order here. And what I would get is that a solution for this linear set of equation, A times x equals 0, is any linear combination such that x equals alpha times 1 minus 1 minus 1, 1. This is x1. This is minus 1 times x2, minus 1 times alpha, that's x3, and then, of course, alpha at the end. Okay. All right. Well, what does that mean? I hope you can still hear me. Well, what does that mean? Well, this is what it means. It means that if I have some observation of this tomography problem, this is x1, x2, x3, and x4, and I want to solve it, well, there is a solution that we kind of found before. There is a solution, but there is some uncertainty because if I add any linear combination of 1, minus 1, minus 1, 1, like that signal, any linear, any scaling of this solution or this image to this image will still give me the same result. So that means I don't have enough equations in order to solve, and I have this uncertainty, and I can just take the solution and add anything to it. It will be a solution. Anything that you add this plus some alpha that will be a plausible solution. So, in some ways I can say, you know what, an image that is, let's say alpha was equal 1, then an image that is 2, 0, and 3 is also plausible, even though the true image is 1, 3, 1, 2. But I just don't know. These are all possible solutions, and I just don't know. I just don't know. So I have an uncertainty. All right. And the reason for it is because my encoding matrix, the one that I chose to do 1, 2, 3, 4 measurement, had a null space. And that was a flawed matrix. I really need another measurement. I need to create a different matrix such that I will be able to perform the operation. Okay. All right. I'm glad. I hope you enjoyed this video. And yeah, see you on Tuesday. Thank you so much.